Good morning. This is your stat sensei, Mr. Spensey, and this will be a hypothesis test using the exam score problem from our warm up. So, in the warm up, it says a college professor has 350 students in a lecture class. She claims that the average score on the final exam is 75. So, that's going to be important. That's my claim out of 100. A random sample of 20. So, we have n equals 20. You can go ahead and write that down. We have a sample size 20 is taken, and the student scores are as follows. And it says conduct a test at the 3% level. So they're telling us in this case alpha equals 0.03 because that's going to be our test region. So let's go ahead and do some work here. So our formula T equals X bar minus mu S divided by the square root of N. So basically, we have the sample mean minus the population mean divided by the sample standard deviation divided by the square root of n. Being S tells us this is going to be a t distribution. That's what distinguishes it from being a normal. All right, if I were drawing a picture of this, well, I would need some information before I could get there. So I'm going to go ahead and input that data, which I already have. So if I go to stat edit, you'll see that I have all 20 data values entered into the calculator. I'm going to go stat calc, one var stats. My data is in L1, so the blue button followed by the number one. And I calculate, and I have a sample mean of 75.8. Please be careful. This is the sample mean. It's not the population mean. We'll come back to that in a moment. And then we need the sample standard deviation, which is 1.5423. Well, what was our population mean? Our population mean is the claim, it's the status quo. So we don't know if it's really 75, but that's what the claim is. So we assume it's right until we can prove otherwise. So when we go ahead and draw this, we're actually supposed to be centered on the population mean. Well, our population mean is 75. Now, in this case, it says differs. That's important. That didn't tell me greater than or less than. It just says differs. And differs tells me we're looking for a not equal. Here we have a X bar of 75.8. So we're looking for a value going this way, and we need to shade it this way as well because this is a two-tailed test. So we want to know the probability it's this or more or this or less, the same amount, the same distance. So really we could have put 74.2, but we didn't get that from the sample. So not equal, because that's what we have is not equal to. All right, so we're going to plug this into our formula. And anytime we're using a not equal to, we have to put two times. So two times probability, two times the probability that t, in this case, is greater than, because that's why we have to double it, because one tail was greater than, but two tails would be both directions. X bar 75.8 minus the 75 divided by S divided by the square root of N, 1.5423 over the square root of 20. So I've now plugged into my formula, and this is if you go to the calculator, if you forgot what it's called, just go to stat test. Oh, it's a t-test. So what is this? How many samples do we have? One sample, t-test. And what are we testing? We're testing means for means. All right, my HO, mu equals, in this case, we believe the professor, and the professor said 75, so the mean is 75. Our alternative is the mean does not equal 75. And for AP stats, this symbol will always be the same. And these numbers will always be the same. The only thing that will change will be the inequality, which in this case, this one will always be equal. So this is always equal. And this will either be less than, greater than, or if it's two-tailed, which we have here, not equal to, and two-tailed was because it said the word differs. All right, so the parameter, let mu equal the true population mean. What were we caring about? We're caring about exam scores, mean final exam scores. All right. Conditions. Well, the first condition will always be random sample. And we need to go back and check. Well, we know we have a sample of size 20, and it says random sample. So random sample of 20, and that was given, and we can put a check mark by it. The next thing we need to do is check the independence condition. Is N less than 10% of the population? Well, in this case, we know that our sample size was 20. We can go 10 times 20 equals 200, and that's less than, she has 350 students, is less than 350. And then we can put a semicolon and go, well, therefore, N is less than 10% of the population. And then the condition that I consider the most important, which is normality. And they could have told us it was normal, but when we read it, they didn't tell us that. They didn't tell us it was normal. They could have said we could have had a sample size of 30 or more. If the sample size was 30 or more, it'd be normal. It's not. So we have to go ahead and draw a graph. So I have my data in StatEdit, which I showed earlier. There it is in StatEdit. So I'm going to press the blue button in the stat plot, press enter, make sure it's turned on, and I'm going to select the first box plot, the one showing the outliers. My data is an L1, so I need to change that to L1 by pressing the blue button followed by the number 1. And I can press zoom followed by the number 9. And I get this graph. Well, I'm going to go ahead and sketch the graph first. And by the way, I'm not very good at sketching these things. So I'm going to sketch the graph and go, okay, it looks something like this. Some of you are saying it looks nothing like what you drew, but something like that. And I have to label it or I have to put a scale on. Well, I'm not very good at scales, so I'm not going to. I am going to title it. So this is exam scores. And I'm going to press the trace feature and go right here and go, oh, min is 73. Arrow 1 over. Q1 is 75. Median, 76. Arrow 1 over. Q3, 77. And then I arrow 1 over and I have a max of 79. All right, so that's great. I did all that, but I'm still not done. I need to now make the say, um, I need to make the statement that there's no extreme skewness or outliers. The box plot is reasonably symmetric with no outliers. It is okay to proceed. All right. Or it's normal enough. All right. Because basically, it is okay to proceed because it's normal enough. I didn't have enough room to write that. All right. So the next thing we need to do is we need to calculate our probability. Well, we've already written our probability. We've already done that part. We've already shown our work. So we just need a calculator. So we're going to go stat test, t-test. I have data. All right. They made a claim of 75. So I need to put that claim in there. My list is an L1, and I need to make sure I have not equal to in there. And we get 2.319. Now, this is 2 times the probability that T, and remember, this is shaded up, so we're going to use the greater than, 2 times probability that T is greater than 2.3195. There's that. Equals a p-value of 0.0316. All right, equals the p-value of 0.0316. So here's my p-value, 0.0316. I have an alpha of 0.03. Well, this is greater than 0.03. And if you're not sure, make them the same length. It helps. 316 is definitely bigger than 300. So our decision is we fail to reject the null. All right? So our statement, our p value is 0.0316, which is greater than our alpha equal to 0.03. What's our decision? We fail to reject the null. Okay. Our there is not, we would say there is if we rejected, but since we're failing to reject, we're going to say there is not sufficient evidence to suggest that the true population mean final exam scores all I did is restate the let mu equal true population mean final exam scores, that the true population mean final exam scores is, then I need to restate the alternative in words, is different than 75. All right. And that's takes care of that one. Appreciate you watching. Hope to see you on the next one. Thank you.